Hello, let's continue with our lectures. Let's talk about automatic reclosing. Automatic reclosing restores a line or part of the network after a fault trip. The goal is fast return to normal operation. After a short circuit, protection trips the breaker. A voltage dip appears and the fault arc extinguishes. If the installation recovers, the reclosing device closes the breakers again. Normal operation resumes if the fault is permanent. Protection trips the breaker again. The reclosing attempt fails and the line disconnects. Most faults are temporary. Because of this, reclosing is usually limited to 1 or 2 attempts. Typical success rate depends on the fault type and location. For overhead lines, successful reclosing reaches up to 60 or 90%. At the lower operating voltage, the success rate is lower. Automatic reclosing applies mainly to overhead lines, cable lines, and individual transformers and line sections. Reclosing usually restores the same network elements that was disconnected. For this reason, reclosing is one of the most effective reserve measures. Timing parameters of the automatic reclosing uses several time intervals. Opening time is the time for a trip command to breaker contact separation. It includes arc extinction between breaker and contacts. Dead time is the interval during which the line remains de-energized. This time allows insulation recover and the arc extinction. Current pause is the time when no current flows through the lines. During this period, the fault arc must disappear. Ready time is the time after reclosing during which the system prepares for possible next attempt. This time ensures the breaker is ready for another trip if the fault resists. If a new fault occurs after the ready time, reclosing logic allows the next attempts. If the reclosing fails repeatedly, the line disconnects permanently. Automatic reclosing improves system reliability. It reduces outage time and maintains supply continuity. Automatic reclosing schemes differ by several criteria. The main criteria is the number of the phases, number of attempts, and the length of dead time. Reclosing by number of phases. Automatically reclosing divides into single-phase reclosing and three-phase reclosing. Single-phase reclosing is the most common method. This is because most faults in power networks are single-phase faults. In this course, only the faulty phase disconnects. Healthy phases remain energized. System disturbance stays small, stability improves. Three-phase reclosing disconnects all 3 phases at the same time. This method applies when the passive selective operation is not possible. Reclosing can be single-shot reclosing, 2-shot reclosing, and 3-shot reclosing. Single-shot reclosing makes 1 attempt. If the fault remains, the line disconnects permanently. Modern microprocessor-based relays allow multiple attempts. In practice, up to 3 reclosing attempts are used. More attempts increase restoration probability. Too many attempts increase equipment stress. Dead time is the interval between breaker operating and reclosing. The first reclosing attempt is usually fast reclosing. Dead time is short, typically value up to 0.5 seconds. If the fast reclosing fails, delayed reclosing follows. Second and third attempt use longer dead times. These dead times exceed 0.5 seconds. Longer dead times allows better insulation recovery. It also reduces the risk of repeated fault reappearance by combining phase selection, number, attempts, and dead time. Automatic reclosing improves system reliability and stability. When selecting dead time for automatic reclosing, 2 conditions must be met. First, the dead time must be longer than the arc deionization time. This ensures that the fault arc is fully opened. Typically, the ionization time ranges between 0.15 up to 0.2 seconds. The dead time must exceed this value. Second, the dead time must be shorter than the breaker ready time for the next fault. If the dead time is too long, reclosing coordination is lost. Dead time must therefore be satisfied longer than arc time, shorter than the break readiness time. Typically, fast reclosing dead time depends on the voltage level and the number of phases. For 3-phase system at 35 to 110 kilowatts, dead time is typically between 0.3 and 1 second. At the 303 kilowatts, dead time is around 0.4 seconds. For single-phase reclosing, typically dead time is about 1 second. Higher voltage system requires shorter dead time. This helps maintain system stability and synchronization. Lower voltage and single-phase system use longer dead times. This improves insulation recovery. Correct dead time selection is the critical. Too short time leads to reclosing into fault. Too long time increases outage duration. Proper coordination ensures successful and safe automatic reclosing. This section explains different automatic reclosing techniques used in the power networks. Substation-side reclosing. In substation-side reclosing, the breaker recloses first with a short pause. The initial dead time is typically 0.3 to 1 second. If the fault clears, normal operation resumes. If the fault remains, a longer time follows, typically 20 to 180 seconds. If the fault still exists after this period, the feeder disconnects permanently. This method is simple and widely used. Reclosing with the sectionality improves fault isolation. During the second dead time, a sectionation switch opens. This separates the faulty feeder section from the rest of the network. After this operation, reclosing restores supply to the healthy feeder parts. Only the faulted section remains disconnected. If the fault persists, additional reclosing cycles follow. During those cycles, more sectionality switches may open. This technique is effective when the feeders include several sectionizing points. It reduces the number of disconnected customers. Directed reclosing applies mainly in the underground or compensated neutral networks. In case of earth fault, the grounding switch closes briefly. This disconnects the faulty phase to earth. The arc extinguishes and the fault disappears. Normal operation condition without interrupting supply. If the fault does not clear, normal reclosing follows. This may include sectionizing or full reclosing. In underground of arc suppression coil networks, air fault current may be small. Protection sensitivity may become insufficient. In such cases, the faulty phase is intentionally grounded or arc suppression coils are switched. This increases fault current to the detectable levels. The protection operates quickly and selectively. After fault clearance, the network returns to the normal operating mode. These automatic reclosing techniques improve supply continuity, limit outage areas, support fast and selective protection operation, adapt reclosing behavior to network grounding conditions. Together, they form an essential part of modern networks. After a fault is cleared, the power system may split into subsystems that operate without synchronization. This situation may occur even in distribution networks, especially when the disconnected feeder contains generators. Loss of synchronism creates special reclosing condition. 3 reclosing techniques are usually such case: asynchronous reclosing, reclosing with automatic synchronization, and reclosing based on voltage absence of synchronization supervision. In asynchronous reclosing, system part reconnects without synchronism. Voltage magnitudes, phase angles, and the frequency may differ. This causes high electromagnetic forces. Large phase angles difference create very high inrush currents. These currents may exceed a short circuit current. For this reason, asynchronous reclosing is allowed only when the connection point has a short circuit power, or the networking impedance limits current peaks. This limits electromagnetic stress, current pause time is reduced. Asynchronous reclosing is usually allowed only for single-phase reclosing. 3-phase asynchronous reclosing is generally prohibited. Reclosing with automatic synchronization. In automatic synchronization reclosing, synchronism is restored between reclosing. Before breaker closing, the synchronization function checks voltage, magnitude, frequency difference, phase angle difference. Reclosing occurs only when the synchronism conditions are satisfied. This method prevents high transition currents and mechanical stress. Automatic synchronization is preferred in networks with the generators. It ensures safe and controlled reconnection. Reclosing with the voltage absence or synchronism suppression. In some cases, automatic synchronization is not applied. Reclosing is allowed when the voltage is absent on the one side of the breaker. Synchronism between two sides is maintained. If the voltage is present at both sides and the synchronism is lost, reclosing is blocked. This prevents an unsafe reconnection. This method is simpler than full synchronization. It still provides protection against the dangerous reclosing condition. Correct reclosing method selection is critical. It protects equipment from mechanical damage and electrical stress. It also maintains system stability after major disturbance. Synchronizing ensures correct parallel connection of the power system parts. It applies when connecting a generator motor or network section to an energized system. The goal is safe synchronization operation after connection. Two synchronization principles exist: self-synchronization and precise synchronization. In self-synchronization, the generator connects to the network without excisions. The rotor speed is close to synchronous speed. After connection excitation is applied, the generator pulls into synchronism automatically. This method is rarely used. Large transient current and voltage dips may occur. System operation may be disturbed for 1 or 2 seconds. Self-synchronization is allowed mainly in the emergency cases. It applies to small generators that must connect quickly. Precise synchronization requires strict conditions at the moment of the connection. 3 conditions must be satisfied. Generator and system voltage must be nearly equal. Generator and system frequency must be nearly equal. Phase angle difference at closing must be close to 0. If voltage is 0 on one side, then synchronization becomes self-synchronization. If frequency difference is too large, synchronization cannot be maintained. This leads to dynamic instability. The most dangerous case is large phase angle difference. Phase angle changes continuously when the frequency differ. For example, with 1 Hz frequency difference, the phase angle rotates 1 full cycle per second. If closing occurs at 180 degrees phase difference, extreme current follows. Such current may exceed short circuit current. Mechanical damage may occur also. Generator shaft may break, turbine, blades, coupling, bearing, or rotor. Because of the risk, precise synchronization is mandatory in normal operation. Automatic synchronization devices. Precise synchronization use automatic synchronizations. Those devices issue the closing command in advance. It compensates for breaking closing time. Typical breaker closing time is about 0.4 to up to 0.4 seconds. Automatic synchronization ensures safe connection. It protects equipment and preserves system stability. Automatic transfer to reserve connected backup equipment when the main equipment disconnects due to fault or outage. Its purpose is to restore supply or keep a technological process running. Automatic reserve transfer is used mainly for 2 cases. First, the power supply restoration. When the main supply disconnects for any reasons, the reserve supply connects automatically. Second, for technological process continuity. If operating mechanism disconnects or a critical process parameter drops, a reserve mechanism connects. Typical examples include pumps, fans, and auxiliary devices in the power plants. Reserve transfer always works in one way. The reserve device connects only after the main disconnects. Reverse operation is not allowed. The command to connect the reserve is given when the auxiliary contacts of the main breaker opens. For pumps, those reserves command may also come from pressure control. By application, reserve transfer automatics are used for power supply sources, transformers, lines, bus bar sections. Each application has specific logic and supervision. By operating principle, reserve transfers device into one-way reserve transfer, two-way reserve transfer. One-way reserve transfer connects reserve equipment only from main to reserve. The reserve does not replace the main device permanently. This method is used when reserve equipment serves only as backup. Example includes temporary replacement during the maintenance, backup operation during fault clearance. A typical one-way application is auxiliary power supply in power plants. Reserve feeders and reserve transformers form a separate supply branch. Two-way reserve transform allows switching between main and reserve devices. Only one device operates at a time. The other remains in the reserve. This method is common between 2 main devices of equal importance. It ensures that one device always remains available. Automatic reserve transfer increases reliability. It reduces outage duration. It supports safe and continuous operation of power system and the industrial process. When electrical interruption of the operating disturbance occurs, the first task is fault handling. The goal is to identify the fault location and fault type. After that, supply to consumer must be restored. Operators receive support from the information systems. These systems show network operation states. They also indicate possible fault location and switching operation. Fault location is often estimated from the measurements. The electrical distance from the fault is calculated from the current and voltage data. Single-phase served faults make fault location difficult. Fault resistance may vary over the wide range. This reduces accuracy for distance estimation. Remote fault indicators are very useful. They show fault passage information along the feeder. These indicators require proper coordination and interpretation. Once the fault location is known or assumed, switching actions are performed. Faulted sections are isolated using disconnectors. Remote control disconnectors are especially important. They allow fast isolation without sending crews to the site. After isolation, healthy parts of the network are re-energized. Supply restoration follows standard operating procedure. Efficient fault handling reduces outage duration. It improves service continuity and network reliability. Clear procedures and relevant information system are essential. When a permanent fault occurs and automatic reclosing is unsuccessful, the fault must be located quickly. The operator must isolate the fault section and restore supply to the healthy parts of the feeder. Distribution feeders usually include many disconnectors. This allows restoration of supply at most consumers. Only a small number of customers remain without power during fault repair. Fault location starts with estimating the electrical distance of the fault. This distance is calculated from fault current measurements. Protection relays send fault data to the dispatch system. The measured fault current is compared with the calculated values, and fault current is calculated in advance for feeder segments. Typical segments length is 50 to 500 meters. Distance protection may also be used. It estimates fault impedance and distance. Typical accuracy of the fault location is about 1 kilometer. The main uncertainty is fault resistance. Its value is unknown and varies widely. Because of this, the real fault may be closer than calculated. This is called positive error. Load current during the fault also affects measurements. If the fault is far from the feeder starts, voltage and load current may still be present. In this case, the measurement fault current is lower. The calculated fault location appears further than the real one. This is a negative error. Additional errors come from current and voltage transformers, measurement devices, unknown network element impedance, and transformer position. In distribution networks with many branches, fault location becomes more difficult. Identifying the fault branches is key challenge. Additional information is required. Operator experience plays an important role. Environmental conditions help fault location. Strong wind often causes overhead line faults. Construction areas may indicate cable damage. Forest area may point to broken conductors. Cable fault indicators provide variable information. They detect short circuit and their fault currents. These indicators send data to the control system. They help narrow down the faulted sections. Except systems can combine measurement data, calculate the fault distance, operation experience. Such systems speed up follow localization. They improve restoration time and network reliability. An effective way to locate faults quickly and accurately on the 6 and 35 kV line is the use of fault indicators. They operate for both short circuit and earth faults. Typically, fault line indicators for cable lines and overhead lines. Operating principle is that in the cable lines, the fault indicators use a current sensors. Often this sensor is light diode system. Light intensity depends on the strength of the magnetic field around the conductor. The indicator receives light through the optical cable. Based on this signal, it detects the presence of the fault current. For each fault, a summation current transformer is used. This transformer surrounds all three phases conductors. It measures the residual current following during the air fault. The air fault sensor is also connected to the indicator light module. For overhead lines, magnetic and electrical fields-based sensors are used. Those sensors mount close to the conductor, typically 5 to 5 meters away. Overhead lines indicators reacts to face-to-face short circuit. Air fault caused by zero-sequence magnetic fields. Their advantage is the easy installation without breaking the conductor. Fault indicators effectiveness depends on the communication. For long-distance radio communication is used. In urban areas, data cables or mobile communication is common. In overhead lines, interference from magnetic fields may affect measurements. To reduce this, current transformers integrate without disconnectors are used. Some fault indicators are simple mechanical or visual devices. They may use mechanical flags, liquid indicators, or light-based indicators. These devices are not connected to the communication system. They require on-site inspection. They still provide valuable information during the fault patrol. The output for a fault indicator depends on this design. In the simplest case, it behaves like overcurrent relay. It indicates only that current exceeded a threshold. To determine current direction, voltage measurement is also required. Advanced fault indicators include both current and voltage sensing. Fault indicators significantly reduce the fault location time. They improve supply and restoration speed and network reliability. In summary, the fault location follows a structured sequence. First, protection relays record fault data. These include fault current, fault type, phase, and feeder state before automatic reclosing. Next, during the first polling cycle, nearby fault indicators generate alarm signals. Those alarms show fault passage along the feeder. During the next polling cycle, alarm information is transformed to the control center. The dispatch system receives the data. The dispatch system analyzes the information. If needed, it sends queries back to the remote terminals. Those queries request detailed status of fault indicators. Remote terminals respond with the current indicator state. This confirms which indicators operate and which do not. The dispatch system then enriches the dataset. Additional information includes substation short circuit power, network topology, operating state of the breaker, and disconnectors. Using this combined data, this distribution management system calculates fault distance. It evaluates available protection and indicator of information. Based on this analysis, the system proposes the most likely fault location. Operators then use this result to isolate the faulty section, restore supply to healthy network parts. This structural approach speeds up fault localization, reduces outage duration, improves reliability and distribution networks. Most medium voltage distribution network faults are single-phase faults. In isolated ground networks, these faults cause small currents. Because air fault current is low, protection may not always operate. Automatic reclosing may also remain inactive. In some cases, the feeder is not disconnected at all. In isolated neutral networks, air faults may cause intermediate arcing. This creates a flickering electrical arc. The arc damages insulation. It increases fire risk. Each arc reignition creates overvoltage. Those overvoltage rise with arc reignition. Overvoltage peak values increase step by step. Table values show that after several reignition, voltage can exceed 4 times nominal phase values. Because of this risk, air faults must be cleared quickly. If transitional resistance is low, below about 100 ohms, fast disconnection is required. This prevents arc development and insulation damage. In other cases, air faults may persist temporarily. The fault location must then be identified before reclosing. To locate and clear air fault quickly, neutral grounding automation is used. When air fault is detected, the transformer neutral is grounded for a short time. Grounding uses a small active resistance. This creates a short circuit. Fault current increases as a result. Protection operates quickly. Fault clearing becomes selective, and fault location becomes easier. In the resonant grounded networks, intermediate arcing is rare. Still, neutral grounding automation may be applied. This ensures fast air fault disconnection, reliable fault location, reduces overvoltage stress. Air fault location is critical for network safety. Correct handling prevents insulation damage and fire risk at the long outages. Correct handling prevents insulation damage and fire risk. Fast and accurate detection of air faults is the most difficult task in distribution networks. Because of this complexity, no single universal detection method exists today. Instead, several complementary methods are used. Transistor current identification. A air fault creates a complex transistor current process. The peak current is often high enough for detection. However, the current strength depends on the phase voltage where the fault occurs. If the fault happens near the voltage zero crossing, the transistor current remains small. In this case, air fault detection becomes difficult. Zero sequence voltage measurement. Another method is zero sequence voltage measurement. Protection operates when voltage asymmetric causes zero sequence voltage to exceed a set level. A typical pickup value is about 30% of the nominal phase voltage. This method detects the presence of an air fault regardless of the location. However, when the fault transition resistance is high, the fault may remain undetected. If arc suppression coil induction remains unchanged, only the faulty phase current changes. This change produces a variation of zero sequence current. The relay detects this change as an impulse. To enhance detection, the arc suppression coil inductance is very slightly. This is achieved by switching parallel capacitor periodically. The switching frequency is 0.5 to 1 Hz. This causes the resulting induction change of about 3%. The resulting zero sequence current impulses is measured by the protection relay. The active power of the zero sequence component equals loss in the coil arc suppression coil. During an air fault, additional losses appear in the faulted phase. Those losses change the zero sequence active power. Active power relays detect this change, however, those losses are small. Reliable operation requires high relay sensitivity, accurate current, and voltage transformers. No single method is sufficient in all cases. Modern air fault protection combines several methods. This improves sensitivity, selectivity, and reliability of complex networks. Several additional methods support air fault detection. They are often used together with the main protection function. In underground neutral networks, the reactive power of the zero sequence component can be monitored. When an air fault occurs, this reactive power increases sharply. This increase indicates the presence of an air fault. The method is not suitable for compensated networks. In those networks, reactive power depends strongly on the compensation level. Arc suppression coils do not significantly affect higher harmonics. This is because coil impedance increases with the frequency. Resonant grounded networks behave similarly to isolated networks at the fifth harmonic, around 250 Hz. Air fault detection uses changes in fifth harmonic current magnitude and amplitude, and isolated magnetic or electrical field. This method improves sensibility during weak air faults. During air fault, the current in the faulted phase differs from their phases. Under symmetric load condition, phase currents are normally similar. By comparing phase currents that the faulted phase can be identified, this method helps locate the faulty feeder. Applying fault indicators for protection purposes is technically possible, however, it requires reliable communication channels. When communication is available, fault indicators improve selectivity and speed. Directional numerical distance protection can also detect faults. It evaluates impedance changes towards the fault. This method works best when the network parameters are well known. It complements other air fault detection techniques. Modern air fault protection relies on combination methods. Each method covers weakness of the other. Together, they ensure reliable and selective air fault detection. In air fault condition, fault indicators operate only when the network neutral is isolated or partly compensated. In fully compensated networks, residual current may be too small for reliable indication. When the air fault current is small, fault location can use transient current oscillograms. Those oscillograms are recorded with a very small time step, typically about 0.001 seconds. Fault location is then determined by analyzing the transient process. Transient process during air fault. When the air fault occurs, the voltage of the fault phase drops, the voltage of the two healthy phases increases. This creates transient process. The transient behavior is clearly in healthy phases. Transient current and voltage, amplitude, frequency, and damping rate. These depend on the network parameters. Fault location. Typically dominant frequencies are faulted phase 100 to 800 Hz. Faulty distance can be calculated from a transient analysis using several methods. First, the differential equation method. The faulty phase voltage and current follows the formula. By solving this equation for inductions and knowing line induction per unit length, faulty distance can be estimated. Second, the Fourier transform method. Transient voltage and current spectra are calculated. Using dominant frequency components, fault disturbance is determined. Third, the least square method. Calculate transient results are fitted to measure waveforms. This method gives the best accuracy. However, it's computationally complex. It may produce multiple solutions. If the transition resistance is below 50 ohms, these methods achieve fault location accuracy about 1 to 2 kilometers. A fault location can be performed without disconnecting the feeder. This is allowed only when the air fault current is small and no electric arc occurs. This is no danger to people. Air fault current must not disturb communication lines. Measuring equipment must not overload. If the air fault lasts longer than 8 hours, phase voltage rises may damage voltage transformers. In practice, fault location allows 3 steps: detect the air fault, identify the faulted feeder, determine the feeder section, locate the exact fault point. Final fault identification is usually performed in the field crew. Analytically, methods reduce search area and restoration time. When a fault occurs, the feeder circuit breaker opens first. This disconnects the faulty feeder from the network. The next task is fault isolation. The goal is to separate the faulty section using disconnectors. Fault isolation must be fast. This reduces outage during the limits, economic losses, and consumers. First halt indicators show that the fault passage remote terminals RTU1 and RTU3 provide status information. Based on the indicator data, the faulty section is identified. Disconnectors around this section are opened. Once the faulted section is isolated, supply restoration begins. Healthy feeder sections are re-energized step by step. The feeder breakers close again. Only the faulted section remains disconnected. Most consumers receive power again. Modern distribution networks use remote control devices. Those include remote control breakers and remote control disconnectors, fault indicators and communicators. The dispatch system coordinates switching operation. Operators supervise the process from the control center. Typical restoration sequence. Firstly, feeder breaker trips to the fault. Fault indicators identifies the faulted section. Disconnectors isolate the faulty sections. Then the feeder breaker recloses. Then the supply restores to the healthy section. This sequence may repeat if initial isolation is incorrect. Importance of fast isolation. Fast fault isolation shortens outage time, reduces customer impact, improves service reliability, limits network stress. Efficient fault isolation and supply restoration are key functions of distribution automation systems. Fault management includes more than fault location. It also covers fault isolation and supply restoration. A switching plan is prepared first. This plan is based on the switching simulations. Simulation consider normal operation and short circuit condition. Simulation help optimize the fault handling action. It also allows estimation of the customer outage duration, energy not supplied, economic impact. The same approach applies to planned switching. When the multiple switching operation exists, network topology can be optimized. Faulty sections are isolated using remote control disconnectors. After isolation, supply is restored to healthy section. If needed, neighboring feeders provide backup supplies. Air faults may also require temporary grounding actions. During the restoration, technical limits are checked. Thermal loading, voltage level, overload risk. With the remote control disconnectors, fault handling can be automated. A typical automated fault handling sequence includes 4 stages. First, fault indicators operates and identifies the faulty feeders. The feeder circuit breaks opens. Second, remote terminals R2, 2, and 3 exchange information. The faulted line section is identified. Third, the disconnectors around the faulty section opens. The faulted section becomes isolated. Fourth, the feeder breakers recloses. If possible, supply is also restored from neighboring feeder. Benefits of automated fault handling. Automated fault handling shortens outage time, reduces customer impact, improves network reliability, and enables fast phase restoration. Effective fault management relies on the accurate data, automation, and clear operating slide. Fault management includes all action needed after the fault occurs. It goes beyond fault location. Fault management covers fault isolation, supply restoration, and switching plan. A switching plan is based on switching simulation. Simulation considers